So in a book, an 1888 book by John Casey, 1888, and I'm going to leave a link in the description, um, a family of polygons is described, which he calls harmonic polygons, which are inversive images of a family of regular polygons. So here's a family of hexagons. These are regular polygons. This is the centroid, and this is their circumcircle. So Casey describes a family which is the inversive image of this family here with respect to a circle centered on a point in the plane. So let's make this be the inversion center. Imagine there's a circle of some radius around the inversion center, and I'm going to light up what Casey calls these magenta polygons harmonic polygons. And their vertices are inversions of the vertices of a family of regular polygons with respect to a circle centered on a point in the plane. So if I move this point in the plane, I'm going to get a different family of harmonic polygons, and these harmonic polygons have many properties. So let's go ahead and look at this whole thing. And of course, because the original family is inscribed in a circle, when you make that family rotate, like so, its inversive image, since circles are mapped to other circles via inversion, this inversive image of magenta polygons, harmonic polygons, is also going to be inscribed in a circle. Its sides are actually enveloping an ellipse, which is not germane to this discussion. We're going to talk about this in some other video, but imagine that there's a caustic to the pink family, to the magenta family, which is an ellipse. Now, what's really germane to this conversation is this point K. It turns out that if you actually draw diagonals connecting opposite vertices of the pink family, in the case of even n, in this case we're on purpose here just looking at, this was an easier construction for me, we're looking at n equals 6. So I can connect these diagonals, and these diagonals are going to concur. Now they concur on a geometrically very special point, which Casey labels as K, and K is also a generalization of what the Symmedian point in a triangle is. So if you think of a triangle, the point of concurrence of the Symmedians, also known as x6, generalizes to the family of harmonic polygons as the generalized Lemoine point, traditionally labeled K. Okay, so you can see here that these major diagonals connecting opposite vertices in the case of even n concur on K. What happens when n is not even? Then you have to draw that elliptic caustic, and K is going to be the point of concurrence between lines of connecting vertices to the points of contact with the caustic. But we're going to cover this in some future video. Let's take n even without loss of generality here. Okay? All right. So, what is this video about? This video is about a generalization of what we've observed in prior videos related to the stationarity of the Symmedian of the inversive image. So let's build an inversive image of this pink polygon here. I'm going to go ahead and light up an inversive circle, which I can place anywhere, a circle of inversion. Okay, I can place it anywhere. So, and I can also move its center along Y. So let's place it in a generic position over here. And I want you to consider now inversions. So a new polygon, which I'm going to light up, this inversive polygon, this orange polygon, whose vertices are now inversions of the pink vertices with respect to this inversive circle. You can change this R to scale this thing up and down, okay, like so. So again, these orange vertices are inversions of the pink vertices with respect to this new circle. Now, since the pink is an inversion with respect to a regular, and the orange is an inversion of a harmonic, you can compose these two inversions and claim that the orange polygon is really the fruit or the byproduct of the composition of two inversions. Therefore, it too is associated. No, the composition of two inversions is an inversion. So it too is also associated with another regular polygon, which is not shown here. And you can argue that this new family here, this orange family, is also a family of harmonic polygons. So this family is also going to be inscribed in a circle. This comes directly from the fact that the pink family is inscribed in a circle, and it's going to have the same properties as all the other harmonic polygons. So namely, if I connect its opposing diagonals, they too are going to meet, and let's try to make this thing more clear. Let's see, they too are going to meet, they're going to concur at an inversive Symmedian point, an inversive K. So you can see there that they too concur, and we're going to call this K inversive. Well, it's already there. We're going to call this K inversive. So it's labeled here as K inv. Okay. Now, a first phenomenon that you realize here is that this Symmedian point, generalized Symmedian point of the inversive family, is collinear with the Symmedian of the original harmonic family and the center of inversion. So if I move my center of inversion, you see that this collinearity is maintained, and that's pretty nice. Okay, I can move my inversion center to the right. I can go to the left here, and I can see that this family of inversive polygons of my harmonic polygons, this new harmonic family, also maintains K stationary, and it is collinear with the original K and the center of inversion. So let's move the center of inversion back to the left, to the right, so we can talk about the phenomenon at hand here. Okay, so what are we going to do now? We're going to make a very interesting transformation here. I'm going to take this pink polygon, this harmonic polygon here, and I'm going to rigidly rotate it about its K. So I'm going to take this harmonic family here, and I'm just going to make a rigid rotation of all its vertices with respect to K. So when you do this, that new polygon is not going to cease to be harmonic because I'm just rotating it rigidly, right? And this particular point here, K, is going to be the K of that new family. So let's just show what I mean by that. Let's rotate that. So I'm rotating this family rigidly about its K. Okay, so this is a rigid rotation. Now, what this video is about is to show what happens to that inversive image when we do that. So here's the inversion circle, which is going to remain stationary. And here's my inversive image of my harmonic polygon. Now let's go ahead and do that. Now look at what happens. When I perform this rigid rotation, the Symmedian point of my inversive family does not move. And this is precisely the phenomenon that we saw with triangles, which is still mysterious. We're still working on proofs. You're welcome to contribute. But it looks like that phenomenon of n equals 3 was actually a special case of this phenomenon. So of course, now I have two stationarities. I can sweep through the harmonics by rotating my regular. So I'm sweeping through the harmonics, rotating the regular. You can see that that maintains the inversive Symmedian stationary. And I can also sweep this rigid rotation about K, which also maintains my inversive Symmedian stationary. So it's as if we have two magical stationarities going on. Alright, so this is the phenomenon, and I'm going to make sure to leave a couple of references in the description, including Casey's magnificent 1888 book, and I'm also going to leave a reference to a paper by, a 1945 paper by Sharp about properties of harmonic polygons. Alright, thank you very much. See you in the next video.